Hello, everybody. Okay, just at the start today, if you go to Brightspace under module tools and surveys, I've created a midterm feedback survey. Just has 3 questions. It basically just asks you what you think is good about the module so far, what you think is bad about the module, and any recommendations you have for improvements. So some of these things I can address within this trimester, and then some of them maybe will affect changes I make for next year. Yeah, if you want to even just check that now, and you can be thinking about it or open it during this lecture, I'd appreciate it. It's only open until tomorrow, and then I'll summarize, tonight, and then I'll summarize any feedback I get next week. So it's fully anonymous. Even if I wanted, there's no way for me to see who posted anything, so you can post whatever you like. So please do click into that now and do it. If you have any questions, as always, I'll just keep the chat open here so you can have a look. I thought I was curious on LinkedIn. I just keep an eye on LinkedIn and Twitter, and I follow a lot of things that show simulations, of course. But I saw there's a postdoc in France put up this paper. So they did a CFD analysis of ducks swimming and why it's good to swim in an inline formation to do with reducing the drag on the ducklings that come behind. So I just thought it's interesting. You can see interesting applications of simulation CFD FEA on LinkedIn or Twitter. So apologies for my voice is a bit crackly. I have cold-like symptoms. Well, I'll try my best. Okay, so today we're going to talk about turbulence modeling. So you probably already, each of you have some understanding of what turbulence is or what we mean by turbulence, but you may have not considered about what different approaches are used for modeling turbulence, particularly in a software like Fluent and OpenFOAM, which we'll use later, so in CFD softwares. So the purpose of these slides will be to, first of all, just make sure we understand what we mean by turbulence, and then talk about some different turbulence modeling approaches that are commonly used. So what is turbulence? So at the basic level, turbulence can be considered as many, or like a population of eddies or vortices. So the word eddy or vortex just means a piece of rotating fluid, that's rotating in one particular direction, whether it's this way or that way. So turbulence is basically a population or a large number of these different eddies or vortices, and they have different strengths and different sizes, and they're often embedded in each other. So you have smaller vortices on the perimeter of bigger vortices. And the one thing that comes up a lot for the definition of turbulence is to do with random or chaotic in nature. So if we were to monitor pressure or velocity or any field characteristic at a particular point in the flow, so for example, in the previous flow, if we had picked a point and then we were in where we think there's turbulent flow, and we were to monitor the velocity, we might get a velocity versus time graph that looks like this, that has what looks like a lot of random noise. So there isn't any particular repeating structures, and it's very random in nature. So that's what we might expect from turbulent flow. But notice that we can define certain things about flow. So we can define, for example, the average velocity at that point. So this U here that's a bit cropped off, we could define that as the average, whereas this U dash is the actual instantaneous velocity as a function of time. So in turbulent flow, the largest eddies are governed by the geometry of the overall system. So if you think about when we calculate the Reynolds number, we need a characteristic length. So what that characteristic length is, it's basically the largest eddy or vortex or piece of circulating fluid that will fit inside our geometry or can be generated by our geometry. So if you have a pipe, the diameter of the pipe will be the largest vortex that could form in a typical flow. Whereas if it's an external flow, like flow around an airplane, well, the largest dimension of the airplane will be the largest eddy that can be formed. So in this case, you've wingtip vortices that form at the end of wings. So they're not going to be larger than the size of the plane itself. So the largest eddy that can be formed, that's just due to the geometry. So that's independent of the flow conditions or the viscosity or density. It's just set by the geometry. So the largest eddy you can have is just based on your geometry. But the smallest eddy you can have, or the smallest vortex you can have, is dependent on the Reynolds number. So the Reynolds number, remember, is a function of density, velocity, and viscosity. So the smallest one is set by a Reynolds number. So as you keep increasing the Reynolds number, the largest vortex size will stay the same, but the smallest ones will get smaller and smaller and smaller. So if you imagine for very high Reynolds numbers, you're going to have very small vortices created. If you go to higher Reynolds numbers, you get even smaller ones. If you go to lower Reynolds numbers, you'll still have the same big eddies formed, but the smaller ones won't be as small. So, so for the Reynolds number, also is essentially gives an indication of the range of scales in the flow. So if it governs the size of the smallest ones and the biggest ones are fixed by the geometry, then basically the Reynolds number, the higher your Reynolds number, the greater the scale of vortices that will be present in the flow. So for a low Reynolds number, the ratio of the smallest to the biggest eddy might be not that large a ratio, but if you have a very high Reynolds number, then that ratio will be much greater. So you have orders of magnitude of difference between the largest eddy and the smallest one. So the smallest one in this case could be the order of millimeters or sub-millimeters, but the largest one is of the order of meters or tens of meters. So the way it works is there's something known as the turbulent energy cascade. So initially, from some external stimulus, so in this case the plane flying, it will impart energy into the flow to generate these large vortices or these large eddies. And that's where all the energy goes. All this external energy goes into creating these large eddies. So what happens is these large eddies would break up into smaller eddies. So from the side of this, you'll get smaller eddies being broken off. So the energy from these larger vortices is transferred into smaller vortices, so the kinetic energy. And then these smaller vortices then will also break up into even smaller vortices. So you get this cascade of vortices starting with big, going to smaller, to smaller, to smaller, to smaller. So at the large scale, the viscous damping of the air in this case, or whatever the fluid is negligible. There's a certain inertia this eddy has that's causing it to swirl around. And the viscosity of the fluid isn't really slowing it down in any way. It's not really absorbing much energy or dissipating much energy into heat. But what happens is as the eddies get smaller and smaller, then the relative effect of viscosity gets larger and larger. So at some point, when the eddies get small enough, then the viscosity of the fluid dominates and takes over the inertia of these small eddies. And at that point, the energy just gets dissipated. Those smallest eddies don't make any smaller ones. They just get dissipated into heat, just friction of heating up the air. So the Reynolds number gives an indication of what scale that this viscous dissipation occurs, and what size the eddies are when they get converted into heat. So we can see typically kind of a classic example of this energy cascade. So on the y-axis we have eddy orbital velocity, so that's the velocity at which they're rotating. And on the x-axis, we have the size of the vortices. So at some point here, the max where the eddies are largest, that's where the energy is supplied from like the airplane or whatever the flow conditions are. So it's not possible to make any larger vortices because that Dmax is just set by the geometry. The largest vortex that can be generated by the geometry, or that can fit inside the geometry if it's internal flow. So you won't get any vortices to the right. So then what happens is these larger vortices, they will split up into smaller ones, and those smaller ones will be traveling at lower velocities, and those smaller ones will split up into even lower ones at lower velocities, and even lower ones at lower velocities, and even lower ones at lower velocities, until some point you get the viscous dissipation, or the viscosity of the fluid starts to dominate. And then at that point, when you get to a certain d-min, a certain small vortices that are going slower, then they just dissipate. So all of that kinetic energy that started in maybe one big vortex has been split into maybe hundreds or thousands of small little vortices, and then they'll just dissipate. And by dissipate, I mean their kinetic energy gets converted into heat. So it just heats up the fluid, basically. So can we estimate these scales? So yes, we can. So these scales are called Magnikov scales. I think I have it on the next slide. After probably a Russian scientist. So you can approximate d-min and t-min. So d-min is the smallest, the diameter of the smallest eddy you will get in your flow, and t-min is the time scale, like the rate at which how long it takes for it to circulate, for example, like how long one revolution takes approximately. So you can write it as a function of the Reynolds number, or just directly in terms of the viscosity, kinematic viscosity here. So viscosity divided by density, the length, and the free stream velocity. And in the same way, so that'll give you like the actual size, the diameter. And the same way, you could also do the same for the time, like in terms of seconds, like the rate at which they're rotating. So consider this example. So I'll ask you to actually do this calculation. If you have a calculator or a calculator in your computer, hopefully you'll be able to estimate this. So consider a car traveling like at a normal, like cruising speed, whatever that might be. What is the smallest eddy that will be generated in the air in the wake of this car? So maybe if you just like to try that, and you can just post it to me, you can post it to everyone, or you can just post it privately to me. I won't read out anyone's names if you post it privately. Just want to give you a minute or two to try this. So the only things you might need, so I'll let you estimate the velocity and the length. And the viscosity, you might not know the kinematic viscosity of air off by heart. You can Google it, but I can just let you know it's approximately 2 e to the minus 5. I think that's meters per second, meters squared per second. So 2 e to the minus 5, you can use for this one, assuming that you do the other dimensions in meters and meters per second. So maybe just try that, at least try the d-min one and post it in, and then I'll show you the calculation. So I'll just give you a minute. Somebody try it. Okay, got some answers. Wait a little bit longer. So if you do these, if you put in the units in meters and meters per second, then this will give out an answer in meters. Okay, I've one answer in here, so thank you to that one person. 2, 3 people, very good, great, thanks. So a variety of answers ranging from the centimeter scale down to the, I'm not even sure what the name is for e to the minus 18 the nano scale or something like that. So, okay, there's a range of numbers here. So possibly would suggest some people need to just check they can use a calculator with exponential numbers. I think that's probably the issue, that maybe making sure you can put in e to the whatever and you're not multiplying the exponentials. But okay, so we've some numbers around the centimeters, some around the microns, and some much smaller. Okay, so let me see, did I do the calculation here? No, I think I have it in the notes underneath. Yeah, so the answer approximately I'm getting, depending on your cruising speed, was the order of like 30 microns. So one of the answers is about that. So if I assume there's 100 kilometers per hour cruising speed, that's approximately 30 meters per second. If you multiply by 1,000, divide by 60 twice, it's about 30 meters per second. I'll just use that. Length of a car, I'm going to say it's about 2 meters. I'm going to take the viscosity about 2 e to the minus 5. So if you plug all of those numbers in on my Mac, I can just do the calculator here. It'll come out 27. That's e to the minus 6. If I multiply by e to the 6, you can see it's 27 microns. So that's 27 thousandths of a millimeter. So these are really tiny. So the diameter of a hair follicle is probably similar to that. It might be like 10 or 20 or 30 microns. So hopefully something you're going to notice, or that will be immediately obvious in this, from a modeling perspective. If we were trying to model flow past a car, if we want to describe these smallest eddies, so if you have a small rotating piece of fluid, for one rotation, you probably need 4 cells, because you can't have a rotation in a cell. You only have one velocity. So you need at least 4 cells to have the velocities going around. So like divide that by 2, like 10 microns would need to be your mesh resolution. So you can see that already. It should be obvious to you that's prohibitively expensive. So to actually do a calculation capturing the smallest eddy that's generated would be very, very expensive to do. If not, it may not even be possible. In terms of the T-min, the rotation time is of the order of microseconds as well. So e to the minus 6 of seconds. So you can see your time step would have to be like of the order of 10 microseconds, and your mesh would have to be of the order of 10 microns to capture all of these. So hopefully that's one takeaway from this, is that will be expensive. So what can we do? How can we deal with this situation? So there's a few different ways to do it. The first way is, like we just talked about, is just to do that. Make your mesh fine enough and your time set fine enough to capture the smallest eddy. So that approach is called direct numerical simulation. It's called direct numerical simulation because we really just try simulate the tiniest eddy, every eddy that's formed. So if we make the mesh finer than that, there will be no eddies because viscosity will just kill them all at that stage. So this simulation on the right is a 2D flow over a box, and this is a DNS simulation, a direct numerical simulation. So the video resolution is not super excellent here, but you can see the resolution involved in this case. So they're capturing the large eddies. So the large eddies are about the size of the box, because that's what it's dictated by, but they're getting broken up into smaller and smaller and smaller ones. And then when the second half of the video zooms in, you can see even in the wake, instabilities in the wake are generating smaller eddies as well, and smaller eddies. And then at some point they get dissipated. So if you click on the link there, I think they explain how long it took to do that calculation, but it was probably using hundreds or thousands of CPU cores running for weeks just to get a 2D simulation of flow over a box. So you can see that this approach, this DNS approach, is not really practical for modeling, for engineering flows. So like designing a car or something like that. So you have to make the mesh resolution small enough to capture this D-min. And this D-min is called a Magnikov scale. And the same with the time step needs to be small enough to capture it. So DNS doesn't introduce any extra fancy modeling approaches. So turbulence is fully described by the Navier-Stokes equations. If you just have a high enough spatial and temporal resolution, it's fully captured by the Navier-Stokes equations. So there's inherent instabilities when you're solving the Navier-Stokes equations, and in their native form, they fully describe turbulence. There's no turbulence model needed. You just have what we've done so far, CFD simulations, no turbulence model, just have a really fine mesh and fine time step. There are some challenges with DNS to do with sensitivity to boundary conditions and things like that, but we're not going to talk about that. So DNS is the most accurate. It describes turbulence. We can directly describe turbulence, but it's the most computationally expensive by far. So from a practical perspective, what can we do? Can we come up with anything that's a little bit better? So the next is something called large eddy simulation. So think about the name for a second, large eddy simulation. So the idea is we just simulate the large eddies, but all the really small ones, we won't have a fine enough mesh for those, but we need to account for their behavior in some way. So what we'll do is, they say is we model those, and by model, they don't mean that the mesh is fine enough to capture them. They basically mathematically model them. So they include a term or some terms, complicated mathematical terms that they add to the momentum equation or to the Navier-Stokes equations to account for the effect of these very small eddies that we're not directly simulating. So if you imagine, if you monitor a flow like this, you'll have larger eddies and then you'll have the tiniest ones. So all of them are captured by a DNS, but LES will only have a mesh that's fine enough to capture the bigger ones. Okay. And we'll only have a time step that's small enough to capture the rotation of the big ones. At some point, when those larger ones break up into smaller ones, the mesh won't be fine enough anymore, but we add a term or terms to the momentum equation, so-called modeling LES terms, that will account or approximate the effect of these smaller eddies. So LES is less expensive than DNS. Obviously, you have a coarser mesh, but it's far more expensive than another approach we're going to talk about, which is RANS. So you may have heard of RANS, or Reynolds Average Navier-Stokes. So we're going to talk about that approach as the cheapest approach next. Often in LES, they call it filtering. So if you imagine you've a spectrum of large to small eddies, so it basically filters out the smallest ones. So it just ignores the smallest ones and it adds a term to account for what their effect would be. So at any one point in space, if we monitor the velocity, you'd see LES would give you this maybe smoother line capturing the big vortices, but DNS would have like every tiny vortex. So it'd have all of this like totally random turbulent behavior. So here's a short video. I always try to give the links on the slides to the videos. So in this case, they were looking at a wind turbine farm. So essentially, like the monitoring maybe the efficiency of the different wind turbines and how they all interact with each other. So this is an LES simulation. So this was also a pretty expensive simulation. So you can see they're quite a large domain, and given the characteristic sizes of the turbines, they obviously have a fine enough mesh to capture some of the key flow features. So they're showing a slice through the domain here, and you can see that large eddies are being captured here. So some of the large rotations of the fluid are being captured. But I mean, for a wind turbine, the size of the smallest eddies will be similar to that car example, for example. So they may be of the order of microns. So they're not using a micron fine mesh here. They're using some sort of LES large eddy simulation approach. So you can see that the wakes of the turbines are all interacting with the subsequent turbine. I'll let the last minute play. Okay, we're just looking at streamlines. Let me see, is there anything else interesting in this video? Oh, releasing particles, seeing where they fly. Anything else interesting? No, okay. So that's LES. So DNS is basically just have a mesh and time step fine enough to model everything. LES, you just ignore the smaller ones and you have some filtering terms, some so-called mathematically modeling terms. So then the other end of the extreme is a RANS approach, so Reynolds Average Navier-Stokes equation. So you may have gone through that before. So the idea with RANS is you're not trying to directly model the instantaneous velocity at any point. Instead, you're just trying to capture the average velocity and the average pressure, the average field. So by average, I mean typically time average. So if you imagine there's this flow over a backward facing step, this is a classic kind of fluid test case. So you flow coming in from the right, it goes over the step, detaching the flow. So you get some sort of vortices being generated and random things like that. I think one of the tutorials was that this week was on this test case. So the true instantaneous velocity field, so this is either DNS or LES, would have a lot of eddies being formed. So at any one moment in time, the velocity field would look a little bit different. But you get to define the average of that in time. So at any moment in time, just take the time average, the average of all the velocity field of all the velocity in time. So for example, LES or DNS would give you this noisy signal, and then just take the average of that. So the RANS approaches basically try to solve or calculate this time average flow field. So it can be time average, or it can be what's known as ensemble average. So they're conceptually two different things, but they're basically the same thing. So imagine that we ran this experiment multiple times, like hundreds or thousands of times. And at any moment in time, like 1 second, we just take a screenshot of all the different flows from like the true like DNS solution, and then just take the average of all of those. So at any moment in time, you could define what's known as an ensemble average. So an ensemble just means you ran this test case loads of times, so to get rid of the average nature, or to take the average. So RANS is less accurate than LES, and LES is less accurate than DNS, but RANS is computationally cheaper than LES, and the LES is computationally cheaper than DNS. So RANS is pretty common to be used in academia and industry. We're running a test case. I think next week you'll do like flow of a car, and we'll use RANS turbulence models. I think we did RANS this week as well in that Pitts Daily case. So RANS are pretty common to use, and they're basically the same. I mean, they're not particularly expensive to run. But the jump to LES is quite a lot. So once you go to an LES simulation, you have to now run multiple time steps, whereas RANS is just one time step, one steady state time step. LES is now transient, so you may run hundreds or thousands of time steps. So immediately LES tends to be hundreds or thousands of times more expensive than RANS. So there's a big jump from RANS to LES. So LES is less commonly used in industry, but it will be used by maybe, for example, like some high-end industries, maybe automotive, but definitely auto sport and things like that. Or automotive. So there are some other in between RANS and LES, a variety of hybrid methods have been defined. So there's unsteady RANS, which is pretty similar to RANS, except you run it in time steps. There's also something called DES, which you've got some experience with. So DES is RANS near the walls, but then it switches to LES in the main part of the flow. So it's just a cheaper version of LES. So this will be more commonly used. And then there's very large eddy simulation. So that's just the really large eddies you capture, and then the medium and smaller ones you don't. So there's a variety of different approaches that are all based variants of this. I'm taking this slide from Gavin Tabor in Exeter. I saw a talk of his at the conference earlier in the year, and I thought he gave a nice mind map of turbulence modeling. So basically, approaches to modeling turbulence. We have RANS approaches, LES approaches, and then DES is a combination of RANS and LES, and then there's DNS on its own. So DNS is just DNS. RANS, and we're going to talk about some so-called eddy viscosity approaches, but there's also alternative approach called Reynolds stress approaches. And then there's all these turbulence models that you may have seen names of or heard about, like K epsilon and K omega SST and things like that. But then there's LES, there's a variety of LES turbulence models as well. So this kind of shows how all they're connected. So it's useful to get a feeling for that. Okay, so now I'm just going to go through the Reynolds average and Navier-Stokes equations, because it's useful to understand in a bit more detail how RANS works, so that when we're setting up a RANS model, which is pretty common because turbulence is pretty common in most engineering flows of interest. So it's good to be comfortable with the foundations of what exactly is happening in a RANS simulation. Okay, so let me mute while I blow my nose. Apologies, no, he didn't want to hear that. So in a statistically steady flow, every variable, velocities, pressures, can be split or decomposed into a time average and a fluctuation about that time average. So U here is the true velocity at any point. So we can define u bar, which is the straight line. It's just the average velocity. It doesn't change in time. It's just the average velocity. And then u prime or u dash, which represents a fluctuation away from that. So you can see the fluctuation up and down, positive and negative. So we can say any variable, whether it's u or p, can be defined as u bar, the time average, plus the fluctuation. And then we can define this u bar for steady runs as the integral of 1 over the length of time by the variable integrated in time. So what is this saying? It's basically saying take the area under the full noisy curve and then divide by the length. So that'll give you the average height. That's all we're saying here. So if you take the limit of this as you look at greater and greater t's, so that get t bigger and bigger. So as t goes to infinity, this will approach some average value. So that's for steady runs. But you can also define something which is an ensemble base. So rather than thinking about in time, you can imagine that you have n different models that are of the same problem, or n different physical experiments or whatever, all of the same problem, and they're all running at the same time. And because the random nature of turbulence, they won't be exactly the same velocity fields or pressure fields, but at each moment in time, you can take the average of all of those. So as the number of these simulations or experiments goes to infinity, you're taking the average at any moment in time. That would give you an average for a U-RANS or a non-steady RANS simulation. So this reduces to this, or to conceptually very similar concepts. So that's just how we define the average. Okay, so then if we're going to take the Navier-Stokes equation, so Navier-Stokes equations are composed of, sorry, my cursor is disappearing, are composed of the, in the incompressible form, are composed of the continuity equation and the momentum equation. So this divergence of velocity is like summing all the flow into a point, say it's equal to 0. So this is the original incompressible Navier-Stokes equation. So let's just sub in velocity field as a time averaged plus a fluctuation. Then we'll take the time average of this equation. So the time average of that equation, the time average of V bar is just V bar. If you just take the time average of a time average, it's just equal to the average itself. But if you take the time average of the fluctuation, by definition, that's equal to 0, because we know that fluctuates about the average. So if you take the average of that in time, it goes to 0. So it means that when we get the time average continuity equation, it just looks exactly the same, except it's just replaced with V bar instead of V. So the average velocity in time, as opposed to the actual instantaneous true velocity. So that's our time average continuity equation. To do that, there's a bunch of different expressions or identities we're using. So like the time average of a fluctuation is 0. The average is equal to the average of itself as well. If you take the average of a gradient or a divergence or curl of something, it's just equal to the curl or gradient of the average. To do with additive, multiplicative, things like that. So if we do the same thing for a momentum equation, and we've our inertia on the left, mass of acceleration, then we've sum of surface forces and body forces. So surface forces in the fluid, we have our viscous forces and our pressure forces. So we'll just plug in the definition of velocity as an average plus a perturbation, plug it in everywhere. Do the same for pressure plus a perturbation, and then we'll take the time average of all of this. So if we do it term by term over here, we know that we can split this into two terms. The average of an average will just be the average itself. The average of perturbation will go to 0. And so that's fine for the first term, and the first on the left, and the first on the right, and the second on the right. But this term here, we'll have a average by an average, which is fine. Perturbation by an average, which goes to 0. But then perturbation by perturbation, if you get the time average of a perturbation by perturbation, it's not 0. So if you don't believe that, maybe just generate two random cycles in Excel, and then random about 0, so their average is about 0, and then multiply them by each other, take the average. So that average won't be equal to 0. So depending on where the peaks are, if they line up, you might get a very positive peak in the perturbation by the perturbation, but you might not get the same one on the negative side. So the average of a perturbation by perturbation, that doesn't disappear. So the difference with the RANS equations is there's just one extra term here in this so-called convection term. So this term here, this perturbation, velocity perturbation by velocity perturbation, is is an extra one. So typically that's moved over onto the right-hand side, this divergence of a time average of a perturbation by perturbation. And this thing is called the Reynolds stress. So it basically looks like you have a velocity by velocity, which makes a tensor, and the divergence of this tensor, it kind of looks like a divergence of stress. So they call this a Reynolds stress. So what this Reynolds stress is, it's basically at the at the larger scale, it's like the force that the smaller eddies impart on the flow. So that's kind of the concept of what this Reynolds stress is. So it's the effect of all these smaller eddies, or actually in the case of RANs, it's the effect of all these eddies on the average flow quantities. So just a note here, this term goes to 0 if it's a RANs case, but it's not 0 in a U-RANs case. So how do we approximate this? Well, one way to do it is using these so-called eddy viscosity models. So this is maybe the most common RANs approach. And there's a variety of different turbulence models within the eddy viscosity realm. So the idea is, well, at a high level, the average velocities and average pressures, when they're going, the fluid's flowing through very turbulent regions with a lot of mixing, from the high level, it kind of looks like or feels like that the viscosity is increasing in those regions. So if you go to a laminar region and then you suddenly go to a turbulent region, because of all the mixing, it kind of, it's apparently seems like it's more viscous. So the true viscosity of the fluid is the same, but if you're not directly modeling those and you just have a coarse mesh and you're trying to account for the effect of all these small eddies, it's like an increase in viscosity in those regions. It's worth reminding you as well that turbulence models are engineering approximations. So the people who came up with these, they were just trying to find things that worked well for the experiments they performed. So they're not exact governing equations or conservation laws, they're just engineering approximations, which means they're not quite correct, but they can be useful. So if you use the wrong turbulence model in the wrong scenario, you could get very wrong results. So the idea for the K epsilon eddy viscosity approach is this Reynolds stress term is described in terms of the average velocity by something called turbulent viscosity. So turbulent viscosity is not a real viscosity, it's just an addition to the real viscosity as a function of these smaller eddies. So it's like the apparent increase in viscosity caused by these eddies, basically. And it's also functioned as K, and that's the kinetic energy of these smaller, these eddies that you're not capturing on the grid. So this is called the Boussinesq approximation. So K here is the kinetic energy of these perturbations, basically, averaged in time. So what these eddy viscosity approaches do is they have a variety of different ways to calculate these K variables. So we're going to talk about K epsilon. K is the kinetic energy of these perturbations. And then when they get small enough, they get dissipated. So epsilon represents, I haven't given the formula for it here, but epsilon represents the dissipation rate. So when they get small enough, they'll be dissipated into heat. So the K epsilon turbulence model tries to directly calculate what this kinetic energy is of these smaller eddies, which are not directly simulating, and epsilon, which is the rate at which they're converted to heat. There's also a K omega, instead of epsilon, they calculate omega, which is another kind of form of dissipation. And there's a variety of other approaches as well. So then in the governing equation, instead of directly using the viscosity, the dynamic viscosity, they replace that by the effective viscosity, which is the viscosity plus the turbulent viscosity, which is not a real one, it's just due to the flow conditions. So the ratio of the turbulent viscosity to the true viscosity is called the turbulent viscosity ratio. So these are things that you can look at in fluent or open foam, for example. So just to summarize, and this can help with some of the quizzes as well, if we were doing a RAN simulation, a Reynolds Average Navier-Stokes analysis, and we're using the K epsilon eddy viscosity turbulence model, then we're going to have 6 governing scalar equations and 6 unknowns. So we've if it's 3D, that is. So we've continuity equation, which is 1 unknown, and then we have the Reynolds average momentum equation, which is 3 scalar equations. So between these, we have 4 unknowns: time average pressure, time average velocity, the 3 components. But K epsilon actually solves for a transport of K and epsilon, so extra equations to try to calculate what K and epsilon are in every cell. So they're scalar equations. So in this case, you have 6 unknowns and 6 scalar equations. So I think there's some questions in the quiz about what happens if it was a 2D simulation, for example. So I'm just going to end with a few slides on boundary conditions in the last few minutes. And this is related to turbulence as well. So I'm just going to talk about slip versus no slip, gauge pressure, and also talk about the flow conditions near a no slip wall and turbulent flow. So once again, these will help you answer some of the quiz questions as well. So first, the easiest thing is just pressure. So we can talk about something called absolute pressure, and that's zero referenced against a perfect vacuum. So a perfect vacuum or close to it, like in space or something, that's zero. And then anything above that or relative to that is the absolute pressure. So maybe this is zero reference here, and then the absolute pressure is just how far we are above that. So that can never be negative. It's just zero is the smallest that can be. Then there's gauge pressure, which is typically zeroed against the ambient air pressure or the atmospheric pressure. So you can see atmospheric pressure is up here in terms of absolute pressure, is that black line. So gauge pressure up to that orange line would be positive, but if it was down to this lower line, would be a negative. So gauge pressure can be positive and negative. It's just relative to atmospheric pressure. So this is typically in all our models, we're just using a gauge pressure, like a relative pressure. And sometimes people might refer to something called differential pressure, and the differential pressure is just a pressure between 2 points. So we won't talk about that. Like, for example, between the inlet and outlet, what's the differential? So this is the difference between the two of them. Obviously, if your gauge pressure at the outlet is zero, then the differential between the inlet and outlet is equal to your gauge pressure at the inlet in that case. So now let's consider walls. So let's imagine a no-slip wall first. So no-slip wall is a physical wall. Like, imagine you flowing over your car, the bonnet of your car, or something like that. So the bonnet of the car, this is the wall, the no-slip wall, is slowing down the flow. So it's actually slowing it down so that any fluid molecules that are right beside it are stopped. Essentially, their velocity goes to zero. So as you take the limit going to the wall, the velocity actually goes to zero. So if we were to plot as a function of x or as a function of y, the velocity away from the wall, like away from the bonnet of your car, we can see it's zero at the wall, the orange profile here, and it's increasing. It's slowed down less and less as you get further away. So then you get to the free flow or free stream conditions. So you get some sort of profile of velocity like that, velocity profile. And so that's Vx. That's velocity is a vector, but I'm only talking about the flow parallel to the wall. So right at the wall, we can take the slope, dv, dx, dy. So take how the velocity in the x direction is changing as we move away from the wall. So you can see it's zero here, and then it's larger here, larger here, larger here. So if we define the straight line up as zero, like the slope is zero, and then it becomes positive and goes to infinity if the blue line goes perfectly parallel to the wall. So based on that slope, we have this velocity gradient by the wall. So Newton's law of viscosity basically just says, well, the stress on the wall is equal to the viscosity of your fluid by that gradient. So you can see the greater that gradient is. So in this case, if you imagine as we increase the velocity of the flow, then the stress increases on the wall. So all no-slip walls will have stress, will experience stresses on them or forces on them from the flow, the viscosity of the fluid going by. Also notice if your viscosity is zero or very low, then you'll experience no shear or viscous forces. The wall won't. So that's shear stresses. I'm not talking about normal here. So the pressure of the fluid will push normally out, but I'm just talking about forces along the wall, in your direction along the wall. So you can see a no-slip wall, a physical wall, can support a shear stress. It can have a non-zero shear stress. In contrast, a slip wall is just a mathematical concept. There's no such real thing as a slip wall in practice. What it is basically like a symmetry plane. So like a symmetry plane, it doesn't need to be flat though, it could be curved. But like a symmetry plane, you can't have flow across a symmetry plane. But a symmetry plane won't slow down the flow like a true wall or a no-slip wall. So if we have a slip wall, it doesn't slow down the fluid, it just stops fluid crossing over. So the mass flow across it, like a real wall, a no-slip wall, is zero, but it doesn't slow the fluid down. So by definition, on a slip wall, the shear stress is zero. So you can see the velocity right by the wall is equal to just inside the wall, or as we move away from it. So this gradient is zero as we move that direction. So the shear stress is always zero on a slip wall by definition. So it cannot support a shear stress. You can still have like a pressure on the wall, but not shear stress. And then just to finish off, I know I've ran over a few minutes. To finish off, we're going to talk about, well, what happens in the turbulent flow. So we had really nice velocity profiles there. But what about in the turbulent flow? So if we look at a wall here, this is a turbulent flow. Apologies, it's a bit low resolution. And I'm going to look over here. So very close to the wall, you'll get no eddies. So you get what's known as a viscous sublayer. So if you go close enough to the wall is going to slow the velocity to zero. So it means if you've any eddies near it, they will get slowed down. So like viscous dissipation dominates. So very close to the wall, you get what's known as a viscous sublayer, and that's like a laminar region. There's a thin laminar region against the wall in every turbulent flow. Far away from the wall, you have this fully turbulent region. And then in between both of those, there's something known as the buffer layer. So in the turbulent region, inertia effects dominate, whereas in the viscous region, viscous effects dominate. And in the buffer region, they're similar in magnitude. So in the viscous sublayer, all the eddies are dampened out and they're all converted to heat, whereas in the turbulent region, they're not. And then the buffer layer is where it starts to happen. So this turbulent region is often called the log layer, and then the viscous sublayer is called the linear layer or linear region. So we have the log region and the linear region, and that's to do with when they've done experiments and done DNS simulations, and they plot the parallel velocity, the horizontal velocity as you move away from the wall. They find it on average follows a linear region and close, it varies linearly, and then it starts to vary according to a log. So we can actually plot that here. So if we plot U plus here, so that represents the velocity along the wall, and then we plot that versus Y plus, which is distance away from the wall, you get a linear region followed by a log region. So why does the linear region look curved and log look flat? Well, that's because we're plotted on a log scale. So if you plot it on a log scale, a log function becomes straight and a linear one becomes curved. So you can see up to around 5 here is the so-called linear region, and from about 30 is the log region, and then in between 5 and 30 is what's known as the buffer region. So there's a couple of things here. One, the velocity. If we were to plot absolute velocity and absolute distance, that's not very useful because we can't apply that to lots of like big cars versus small cars versus high velocities versus low velocities. So they normalize the velocity with respect to some flow conditions, and they normalize the distance away from the wall with respect to some other flow conditions. So this Y plus value is the normalized distance away from the wall. So it typically defines the distance to the first cell. So if your first cell is at 30 or greater, you know the first cell center is in the log, or the log region at the turbulent region, whereas if it's in less than 5, you know it's in the linear laminar region. So if you can afford to refine your mesh and put the first cell in the linear region, then it should be able to approximate that slope at the wall, the gradient at the wall, so you can accurately calculate the drag. But typically that will be very expensive, even for RANs. So often you can only get the first cell to be in between 30 and 300 in terms of this Y plus, this normalized distance. So in that case, people have developed something called wall functions. So they assume this profile, they analytically embed this profile into the first layer cell, and then they calculate the slope based on this. So rather than just taking the velocity of the wall minus the velocity in the first cell divided by the distance, they instead embed the numbers directly into this log formula, or this linear log formula, to do the calculation. So these wall functions, the standard ones, typically only work well when you're in the logarithmic region, and then they're not really needed in the linear region. In the buffer region, they don't work that well. So there are improved wall functions as well. But that's it. So that's a very light touch on what wall functions are. But if you go to do your mini project in like RANS flows, you might look into those more. And in particular, if you're doing your thesis project, you'll need to understand the different types of wall functions and when it's appropriate to use them. That's it. Apologies for running over a few minutes. I'm going to hang on. So if anybody has any questions related to this, or anything related to the labs, or anything related to their maybe mini project or anything else, I'll hang on. I'm happy to have a chat. And I can make a breakout room if you wanted to have a chat in private as well. So thanks very much, and hopefully you got something from this lecture and enjoy the weekend. And I'll stop recording as well.